Hello again, everybody, and welcome to Environmental Sciences 347, Lecture 9 in Climatology. Now we're going into paleoclimates. Basically, we want to know what the climate was like before we were here. So, how do we know what the climate of Earth was like before there were instruments, or for that matter, people? Instrument records only go back to the 1870s, so we need to figure out some other way around that. And for those, we use proxies or other types of geological records that will point us in the right direction. And there are four big ones: trees, mud, corals, and ice. Mud, sometimes you'll hear called sediment cores, but basically it is mud. So why do we do this? Well, we want to improve our understanding of what the current climate's like, to figure out how it responds to different external and internal stimulus. All right, give us a true perspective on what the current climate is like. Give us some inkling of what is going to nudge the climate one way or the other based on what's happened in the past. So that's going to require some kind of quantitative or numerical link between the response and the forcing. So let's start with the trees. We look at tree growth rings. That's something you probably remember hearing about in grade school. A year's growth of wood basically shows you how the tree handled one year. The number of tree rings shows you how old the tree is, but you can determine how much the tree has been stressed by the color of wood, the thickness of the rings, and any number of other factors. But one of the things to remember is that not only does it tell you the age of the tree, it shows you if there was drought. It shows you temperature. And you have to go back and look at a lot of correlations between what ancient trees look like and what current trees look like. And that's called cross dating. The width of tree rings generally decreases as the trees get older. Trees grow very rapidly at first, so you're going to get these larger rings as there's more rapid growth when the trees are younger. And then just thinking about concentric circles in a tree, over time, those tree rings are going to get smaller. So when we know that, understand how different species of trees react, we have to realize that the thickness and the density of the tree rings are sensitive to moisture stress. And these are the things that we use to help construct these chronologies or these proxy measurements of tree rings. Pollen profiles, and this goes back to the mud. All right, whether it's ponds, bogs, marshes, swamps, pollen in time piles up. All right, if you think about every spring, and if you've spent some time in the southeast, you'll know this for sure. Every spring you get this pollen over top of everything for a few weeks, or at least a few days. All right, over 20,000 grains per cubic centimeter, so it's a lot. It's a lot. But the types of pollen change through time. The abundance of pollen at different species at different depths as sediments begin to pile up and pollen is trapped through time at different levels in a sediment core at the bottom of some marsh or pond. We get some kind of an idea of what type of plants were around, not necessarily plants in the water, but what kind of plants were around. All right, and we're sending their pollen everywhere. Some of the pollen wanders over the lakes, it settles, and ultimately goes down to the bottom where it just stays. And then you get more sediment and stuff over top of that. So it all piles up. So you basically dig down into there, pull up this big old chunk of mud, and you look down at what kind of pollen is in that mud sediment, right? And see what kind of vegetation was around many, many years ago. I give you a continuous record of sedimentation, some places as back millions of years, not just a few thousands of years. Again, depending on the environment that you're in. One of the other ways we could tell what the temperature was like, not just looking at what kind of vegetation was out there, but what the temperature was like by looking at oxygen isotope analysis. That helps tell us what the temperature is. I'll speak more to that point a little bit later. Also, if you've ever been caving, you think about stalagmites, stalactites, those things. Technically speleothems, dripstones. They're calcium deposits, calcite deposits, limestone caves. All right. And it's the same thing. you've got these things building downward from the roof, and you look at, and there's water in those. That's why you have the calcium deposits and the groundwater coming down. You look at the isotopes in there, the oxygen isotopes in the water there. And then, of course, corals. Coral reefs are the most productive habitats really on the globe. These can extend hundreds of meters, yards above the seafloor, but then hundreds of kilometers, miles if you will, along the shoreline. They don't typically go back as far, but our records go up to about 400 years before present. Part of the reason for that is they cannot tolerate prolonged exposure to massively high or low temperatures or big fluctuations in the temperature. So, as you might have heard in the news, small changes in sea surface temperatures threaten coral reefs. But much like trees, corals have growth rings that can be used to reconstruct past variations in the climate in maritime climates, the tropics and subtropics. So remember how important the tropics are to the global temperature patterns. That's where so much of Earth's energy is, in the tropical regions, especially tropical oceans. Lots and lots of heat energy. It takes a lot of energy to raise the temperature of water. So this is where you have a lot of Earth's stored energy, if you will. And this also folds back onto understanding how El Nino and La Nina events play out. Glaciers, ice is the other thing. And this is one, I'll tell you, I'm a little more personally interested in. These are the ice cores from Antarctica and Greenland ice sheets that take us back through the Pleistocene ice age. Effectively, and we'll talk about how glaciers form in a minute, but you go to a glacier and you just drill down the thing, and then you pull up a massive ice core, and you go back and look at layers in the ice core like you do tree rings, because there's little bits of dissolved air or air bubbles in that ice core from the oxygen and nitrogen and CO2 and all gases that were in the atmosphere at that time. Put that in a vacuum chamber, you run a spectral analysis on it, and you can tell very high precision what the constituents of the atmosphere were at that time. And this can be done very, very accurately 400,000 years into the present. So what we see there is the carbon dioxide measurement. And this is an old graph back to 2007 when the parts per million by volume was only 383. Now it's over 410 because we keep pumping CO2 to the atmosphere. Going way, way back is a little more challenging at true, let's call it geological time scales. I mean, the climates of geological time are a little more complicated. And geological time, you break down to all these eons, eras, periods, epochs, and all these things. And don't stress about all the names of these. Some of these will sound more familiar than others. The Cretaceous was basically kind of the end of the dinosaurs. We're into the Holocene now. So, remember some of the big ones. The Holocene is where we are now. We're in the Holocene epoch now. Before that was the Pleistocene, about more than, basically before the most recent ice age. But some of the terms you'll hear the most, and when you talk about how hot it's been in the past, the Eocene was a very, very warm time in Earth's history. So these are times that are a few million years ago, and then several million, hundreds of million years ago. We've got continents in all different locations. You've got mountains that haven't formed yet. So, that's way, way back. But those are geological processes that really don't affect us too much in the here and now. So just briefly to roll through these things, you can go back and look through bedrock as a widespread source of geologic and climate information. Think about how active volcanoes were in that time, because the rocks that comprise the Earth's crust are three types. You might remember these: igneous, sedimentary, and metamorphic, depending on what kind of environmental conditions they formed. Cooling and crystallization of the molten magma gives you the igneous rock. So then these igneous rock forming processes affect the chemical composition of the atmosphere. They can contribute to climate change and the carbon cycle. We talked a little bit about that a few lectures ago. but you have a more active volcanic environment, you are going to have an obviously very different climate. And you can look at what your concentration of different rock types are, igneous versus sedimentary, and get an idea. Sedimentary rocks basically are rocks that are going to go weathering, exposed to rain, gases, other fluctuating temperatures, then they compact. And so you have sediments compacting to form rock, thusly sedimentary rock. And these are forming, it takes a lot longer for these to form versus just say igneous rocks. And then of course you start getting into metamorphic rock, which is even older kind of rocks. So they've been exposed to pressure, heat, chemically active fluids generally for a much longer time. So in general, your igneous rocks are a little newer, your metamorphic rocks or tend to be a little bit older. So for those really into it, geomorphology is a scientific study of landforms on the Earth's surface and the processes responsible for their formation. So climate can play a role in those, but you've got to go way, way back. And these are things that take a lot longer to process, a lot longer to happen when we talk about geological timescales. A couple other things, varves are thin layers of sediment that are deposited annually in a body of still water. And this is kind of similar to what we talked about before regarding mud and sediment cores and that type of thing. But the absence of bedrock and plate tectonics help complicate reconstruction of past climates in those much, much longer time frames. But there is some available evidence to support conclusions regarding the climate over geological timescales. But again, we do know there have been massive changes in the past, but on the scale of millions of years, not a couple of hundred like what we're dealing with at anthropogenic climate change or man-made climate change. There is sufficient geological evidence to support bigger climate fluctuations about 570 million years ago. This transition between the Precambrian and the Phanerozoic area, basically when you've got the earliest shelled animals to present. Abrupt changes between cold and heat and the South Atlantic rock layers that formed in tropical climates are over top of glacial deposits. So that's why we know that things have not been static. There have been big fluctuations in time because rocks that don't seem to go in one place can be found in another place, and fossils of trees and leaves are found under a couple of miles of ice. So we know that there are big fluctuations in the past. And when we think about it in terms of millions of years ago, you may remember hearing about Pangea 250 million years ago when we had just one kind of supercontinent over top of on the Earth, and you've got two big oceans on either side. This is when the dinosaurs show up, just wandering around Pangea, and then the continents start to drift apart. The whole plate tectonic thing. 66 million years ago, we get a comet hits the Earth. Dinosaurs go extinct because there's obviously a big amount of climate change when you have a comet or an asteroid hitting the Earth. All right, so you're putting all this explosive dust into the atmosphere and the whole planet cools, plants die, and then the dinosaurs can't eat the plants and they're all gone. So we know these kinds of catastrophic events do happen in the past. So right before that time is the Mesozoic, 245 million years ago to about 66 million years ago. That's when there really wasn't much ice at all on Earth. It was generally warm. And during its peak in the Cretaceous period, global temperatures were about 11 to 14 degrees warmer than now. Okay? And that's when the dinosaurs were running all over the place. So that's a lot warmer. But when we think about hot, it's not 30 or 40 degrees warmer. It's only 11 to 14, 10 to 15 in terms of a globally average temperature. And remember, global average temperature right now is about 60 or 61 degrees Fahrenheit. So when we think about what's the global average temperature, this is running about 71, 75 degrees Fahrenheit, globally averaged. So plate tectonics on this time frame has not been a major factor in climate change over the past 2 million years. Again, 66 million, and before that with the dinosaurs, yes, continents were in a different configuration. But more recently, if you will, the continents have generally been in their current configuration. And these last 2 million years, approximately, have favored the development of pretty large glacial ice sheets. In fact, technically, we're in the midst of an interglacial right now. We are in a cold Earth period, if you will, but time scale is everything. And we have to remember that humans have not been around very long at all when we look at the entire history of Earth. So from a historical perspective, the whole idea of glacial theory has only been around for not quite 200 years. All right, that there have been multiple advances and retreats of glacial ice over the past 1.5 million years. So with all this talk of glaciers, what are they? I mean, they're ice, but most people don't know that glaciers are moving. They're just moving really, really slowly compared to what we think of as things moving along. But glaciers do flow, and they do flow basically to the sea. They're a mass of ice that flows internally under the influence of gravity. And it's the second largest reservoir in the global water cycle, and the single largest freshwater reservoir on Earth. Think about all the ice, freshwater ice, sitting on Antarctica and sitting up in Greenland. All right. The large scale climate change is responsible for variations in the Earth's glacial ice cover. That is a very good representation of how hot or how cold the Earth is when we look at how much ice is sitting on the Earth at any given moment in time. Now, glaciers develop where snowfall in a year exceeds the snow melt. And as that happens over many years, your glacier begins to grow. All right, so if you have a winter where you have a bunch of snow coming down, your summer is particularly hot, your snow doesn't melt. So in the next winter, you get more snow on top of that, and then it doesn't melt in summer. Then you get more snow on top of that. So over successive years, dozens to hundreds of years, you start building up a glacier. Now, there are two types of glaciers depending on what part of the Earth you're on. There are the temperate glaciers, where the internal ice temperature rises during the year. And these are the ones that you think about Glacier National Park in Montana. These are the ones in South America. Then there are polar glaciers, ones that the temperature remains below the melting point throughout the year. So there's almost no meltwater generated. In other words, even in Greenland, there is a little bit of melting during the year, during the summer, but then it freezes back over. One of the things we're starting to see, though, is the melt season in Greenland is getting a little bit longer, and we're getting a little more liquid on top of that ice sheet every year. So the climate system, what's the net climate system? Is it net warming? Is it net cooling? Is going to govern the exchange of heat energy and ice mass between a glacier and its environment. All right. So the ice mass is added. Basically, when you get more snow, then you got melt. All right. And ice mass is removed when you got more melting, then you got snowing. So that's the basic principle of glacier developing or retreating or melting off. For example, Greenland isn't all going to melt away in 150 years. That Greenland is slowly melting. Unfortunately, the melt is accelerating. But when we say accelerating, nobody thinks Greenland's gone in 100 years. That's not the time frame that we're talking about at all. So the difference between the ice gain and the ice loss is called the mass balance. If it loses more ice than it gains, it's negative. If it gains more than it loses during the course of a year, it's positive. So the glacier thickens and expands. So it's kind of intuitive. So glacial climates, or the colder climates, will favor a positive mass balance, or glaciers growing. Interglacials favor a negative mass balance. So interglacial means in between glacial periods, which means it's a little bit warmer, so you're losing mass at your ice. And we've seen in the Pleistocene the climate shifting back between glacial and interglacial numerous times. There have been times there have been more ice, there's been times when there's been less ice, but there's generally been some ice around for a while now. Now, the reason this is important, not just because, wow, it's cold here, but has big implications on sea level. All right, so if you've got all this ice that's a couple miles deep over Greenland or over Antarctica, all right, and that melts, well, where does it go? It melts into the ocean. So just like taking ice cubes, putting them in the water, it raises sea level, all right? The floating ice doesn't raise sea level, so sea ice that kind of comes and goes each year doesn't mess with the sea level that much. But, you know, if I've got Greenland melting into there and then that all melts, the waters come up. So that's a very short version. Okay, so glacier ice has important implications for sea level. Because think about it, if you're evaporating water off the ocean and you're turning it into snow when you're building a glacier, your sea level is dropping because you're basically moving ocean water into the atmosphere as snow, and it's so cold, it's snow, you build a glacier, sea level drops. And of course, it works the other way around. You just melt all that stuff back out, and your sea level rises again. The other thing about sea level rise isn't just melting glaciers, but the water temperature itself contributes to sea level rise. Water expands like many things when heated. I mean, not massively, but water expands when heated. And when you've got a very deep ocean, tiny bits of expansion do add up. All right? Water expands when heated and contracts when cooled. It contracts the most down to about 39, 38 degrees Fahrenheit. Then it actually starts to expand as the lattice structure begins to with ice, because ice is actually less dense than water. It's one of the few substances in the universe that as a solid is less dense than liquid because of the lattice structure of the molecules. That's another story. But in general, water expands when heated once you start getting past about 4 or 5 degrees Celsius. So let's think back to the most recent glacial maximum, and just about North America. This is about 15,000 years ago, right? So in geological time, not that long ago. This is what North America kind of looked like, about 15,000-ish years ago. This ice sheet was called Laurentide ice sheet, covered effectively all of Canada, going to the northern part of the plains of the United States and covering a lot of the Northeast. You know, Chicago, New York, Boston, Detroit, they're all under the ice. All right. Then it begins to retreat. And that leaves a lot of things behind. So you have glaciers that advance, you have glaciers that retreat, and that really affects the land beneath them. When the glaciers advance, they do a lot of erosion, and then when they retreat, they leave a lot of water behind. I mean, that's why we have the Great Lakes. That's why Minnesota is the land of 10,000 lakes. That's why there's so many lakes in Manitoba into Canada, because you have retreating ice. They also lead to these meltwater streams. They leave deltas and sediments and things like that. So the lakes that we know of from the Great Lakes and northward are largely in place from retreating glaciers. So then we look back at larger term planetary temperature trends, which sounds something like out of a sci-fi movie. All right, but know that the temperature of the planet has gone up and down a lot. This leads us back to the oxygen isotope thing. Right? Oxygen as we think of it is 8 neutrons, 8 protons. So it has an atomic number of 16. But there's a tiny amount of oxygen 18 out there. It has 2 extra neutrons, so it's a tiny bit heavier. All right. We can examine the differences in those oxygen isotopes, the amount of oxygen 18 versus oxygen 16 to get a handle on what the planetary temperature was going back hundreds of thousands to perhaps millions of years, right? Because if you have a hotter atmosphere, you can effectively evaporate heavier water, heavier oxygen, water that has, it's H2O. So the O there is O18. It's not all O18, but there's more of it, okay? So thinking back a little bit to the Laurentide ice sheet, this was kind of the beginning of what we think about as human civilization as that ice fades away. Now, there were humans out there during the Ice Age and before that, to be sure, all right? But in terms of civilization as we kind of think of it today, modern agriculture, that's a very new thing. Once the Laurentides, the ice sheet finished melting about 5,000 years ago, which is really not that long ago at all. That link there will take you to a computer simulation of how the ice sheet evolved from about 25,000 years ago until it finally melted away. There are, again, you can go back any different number of lengths of time to see how these changes in temperature played out. Where you want to go thousands of years, hundreds of thousands of years before present, you can look at the glacial ice volume there on the top left, or thousands of years before present, up to 160, or just 16 thousands of years. There are always these small fluctuations within the mean. Now the fluctuations there on the top are largely orbital cycle, what we call Milankovitch mechanisms. These are governing how solar energy is coming into the planet, or how it's just being distributed across the planet. All right. When you go back and watch this, when you go back and load the slides, you look at these slides on your own, you'll see these are animating GIFs. All right. The Earth's orbit is not a perfect circle, it's an ellipse. And there are changes in the eccentricity of the ellipse on 100,000-year cycles. You're taught that Earth's orbit is tilted Earth's axis is tilted 23.5 degrees from the vertical, which is true right now, but actually fluctuates a little bit between 22.5 and 24.5. All right. And then the direction that the axis points in space wobbles like a top. All right, so, and that's in a 26,000-year cycle, meaning 13,000 years from now, July will be winter in the Northern Hemisphere. So these affect the distribution of solar energy and are largely responsible for kick-starting warming and cooling periods. They're not entirely responsible, but they kick-start it because this changes how solar energy comes into the Earth in different places. That in turn changes the temperature of the ocean. Changing temperature of the ocean will outgas carbon dioxide, which is a feedback mechanism because that's a greenhouse gas. So these are the things that govern climate on these dozens of thousands of years scale. The polar amplification you heard of is the increase in the magnitude of temperature change with increasing latitude. Basically, polar areas are more sensitive to climate change. The infrared effects are more important than the solar effects. What does that mean? All right, so we know that in the summertime, where we are now, it's hot, and in the wintertime, it's cold. But you can still get some warm spells in the winter. You don't really get many cold spells in the summer unless you lose a bunch of sun. Right? So the infrared effects, remember the ground heats the air. Sun heats the ground, ground heats the air. So the effects of the warming atmosphere, the greenhouse effect, are more pronounced in places that don't get a lot of sun to start with. the poles, winter, places that are cold, are going to be more sensitive to changes in the infrared part of the spectrum because they don't get as much sun. This is why the poles are warming more rapidly than the rest of the world because they don't get that much sun to begin with. The equator is not warming as fast as the poles because they get sun all the time, and that component of the temperature balance, the temperature equation, is much more driven by solar. Since the ice age, if you will, ended 15,000 years ago, there have been a few relatively warmer and cooler periods. The Younger Dryas was a relatively cool episode 10 to 11,000 years ago when the glacial ice started to change drainage patterns, weaken ocean currents. That changed the distribution of energy. But then as we came out of the Younger Dryas, we started seeing civilization as we know it begin to develop. Glacial ice is withdrawing from North America. It leaves the Great Lakes behind. So you start having a climate that is more consistently warm during the summer because your glaciers are going away. So agriculture starts to develop. You're not in a hunter-gatherer situation anymore. You can start planting crops and you can feed more people and you can develop civilization. So since then, in this period we call the Holocene, right, the present interglacial, effectively the last 10,000 years, right, there has had a fairly consistent spatial and temporal variable temperature and precipitation. But it's a climate that you can quote unquote count on. You're not going to have massive variations. We haven't had massive variations. Certainly there have been variations in the last 10,000 years, but they have not been massive. Okay. The medieval warm period, it was a little bit warmer, but there were other parts of the world that were not as warm because our records are a little bit better in the medieval part of Europe. But then we had the little ice age right after that. But those are very small fluctuations. Those are climate variabilities. The medieval warm period, the little ice age from 1000 to 1900. Those are climate variabilities. Those are fluctuations within the long-term state. Okay, those last a couple hundred years, but not a few thousand. So the medieval warm period is defined as this area between about 950 and 1250 AD. Positive temperature anomalies, but we also think there was a lot of drought at that point. But there aren't very good records from the southern hemisphere in the tropics. This period was very short, and we don't have good geological or proxy records for that short of a time frame in the southern hemisphere and in the tropics. So we don't think the medieval warm period was a dominant global warm period. Same thing with the little ice age. It was this period after, between 1400 and 1900, when the average global temperatures were lower, glaciers began to grow in alpine layers, alpine areas, and start to kind of grow downward from mountaintops toward the valleys. And this, when it comes right after the medieval warm period, it's quite a shock to the people who were living during that time. So when we think about the climates of the most recent 1,000 years, we have the medieval warm period and then the little ice age. Neither one of these was comprised of sustained warming or cooling. The sediments and the ice core data that we do have from this time both point to substantial fluctuations in the decadal every 10-year scale in both temperature and precipitation, right? So, medieval warm period, little ice age, those are climate variabilities. They did not reach true climate change, not sustainable in a certain direction. We could think of coming out of the interglacial 10,000 years ago as a small climate change, again, compared to the entire planet, all right? But when we were in the last glacial maximum there, again, 15, 20,000 years ago, the average temperature was about 10 degrees colder than today. So again, you think about the ice age, you go, well, how cold was it? Remember, the average temperature today is about 60. So even with all those ice sheets covering all of Canada and the northern tier of the United States that we know them today, the average global temperature was about 48 to 50 degrees. All right. There wasn't ice at the equator at all. Okay. But there was a lot of ice North America and Asia for sure. Okay, with that, we'll stop. Next time, we'll talk more about the instrument records, basically since the 18th century, and severe weather. When we talk about severe weather, that's something very specific. We're talking about damaging kind of weather, tornadoes, thunderstorms, that kind of stuff. So we'll get into that next time.